Okay, this is Scott Sanford. Today we're going to do the SARE Energy Conservation Series. We're going to look at pipeline systems for irrigation, and today will be presented by Bill Krantz from the University of Nebraska, Lincoln, and we're going to hand it over to Bill.
Thanks, Scott. Today we wanted to follow up and provide the third session that would deal with conducting energy audits for irrigation systems and how one might estimate what the energy conservation might be for doing different sorts of things. And today we're going to be talking specifically about the pipeline distribution systems and the design and selection of equipment for that. So as we look back at the same image that we've been using for the last couple of presentations here, there are some factors that are under the control of the operator in terms of how many inches of water are applied and how efficient the system might be, but there are some things that are also out of our control and are based upon the field and the system that are already out there. Today we're going to concentrate on the pumping pressure for pivots section up here, and there's a lot more involved in this than what is included in this part, but we're going to kind of talk about the different components of the pipeline system to get the water from the water source to the irrigation system and the distribution onto the field site. So the outline for today's presentation includes a couple of things. First, we're going to talk about what happens if we just decrease the overall operating pressure of our water distribution system and how much energy can we save by doing that. We're going to talk about some basic hydraulics in terms of what the pipeline design should be in velocity and friction losses and water pressure ratings and that sort of thing. We're going to do a little bit of the mainline design, and we're looking at diameters and how large the velocity or how high the velocity is in the pipeline. We're going to do a little bit about the friction loss estimation in the whole system and try to figure out if we change the pipeline components, how much energy we might save by reducing the friction loss. And then we're going to do a little cost comparison at the end to compare two different scenarios to try to give you an idea how one might do this for producers. As you look at this is an image that I've used in the pumping plant portion of our discussions here. And across the bottom of this graph, we have pumping depth, or how far we have to move the water to get it from where it is in the ground to the soil surface or outlet of the pump. And if we look at the cost per acre inch of water applied, we can come to some idea of what that overall cost is going to be. Today I'm using an 80% performance rating on the pumping plant, which is a kind of a long-term average value that we found in testing these systems out in the field. And so if we look at a system that pumps from 200 feet below the surface and is delivering water at 60 psi, or the outlet pressure of the pump is 60 pounds of pressure, we are just about right on $2,000 per inch of water applied. So a lot of money spent to distribute the water. If we then look at a different alternative where the irrigation system now, the pressure is reduced to 20 psi, the pumping lift should not be changed in this as long as the flow rate remains the same. So as we do that, we're going to drop now from the $2,000 down to about $1,450 to put on an inch of water. And so this tends to accumulate those savings for every inch of water that we pump. So the more water, obviously the more water we pump on an annual basis, the more savings we could get from that. So let's look at an example then of how we might utilize some of that information to estimate how much energy we can save and how many dollars we could potentially save in production costs. So look at an irrigation system that has 125 feet of lift, operating pressure of 75 psi at the pump outlet. We're irrigating 130 acres. Average application is 12 inches or 1 acre foot per year. And I'm using today the $4 per gallon of diesel fuel. Oops. Went backwards here. Okay, so if we look at this chart that we used in the pumping plant discussion, this chart is set up to come up with a number for how many gallons of diesel fuel it should take to pump an acre-inch of water if the pumping plant itself is at 100% of the Nebraska pumping plant performance criteria. Now, this would be essentially the best we think irrigation pumping plant could do based upon the numbers that we're currently using. And as I mentioned in the pumping plant performance discussion, we're in the process of revising these numbers, and we should be able to do it for less than what this table shows. But we're going to use the table today, and if we have that irrigation system at 70 psi, we're going to go horizontal in the 125 feet of lift row over to the column that's under 70 psi, and we see the number here of 2.61 gallons of diesel fuel per acre inch. So if we do some of the math, then we have to determine how many inches of water are pumped each time. So if we do that, then we're going to come up with a number here of 1,560 acre inches. That's 130 acres times 12. That's the total number of acre inches we're pumping with our irrigation system on an annual basis. If we then take the 2.61 gallons per acre inch requirement times that value, and it tells us we should be able to pump that irrigation water then for usually 4,072 gallons of diesel fuel per year. We multiply it by the cost of diesel fuel, whatever that might be, and we come up with a value of $16,286 here using $4 per gallon of diesel fuel. So a lot of money spent to apply irrigation water to the field in this particular scenario. If we want to consider what our costs would be if we pump water at 50 psi instead of 70 psi, we come up with we have the same basic factors that we start with, but now when we go to the table, we use the same 125 foot of lift, but we're now looking under the 50 pounds of pressure rating here, and that would indicate that we would come up with 2.19 gallons of diesel fuel is what's needed to pump that irrigation water. So we do the same math we did before, and we come up with our 1,560 acre inches. We multiply the 2.19 by our 1,560, and we come up with our 3,416 gallons of diesel fuel in this particular case. And finally, if we do the math to multiply by the cost of fuel, you can see that we're at $13,666 to pump this water on an annual basis. Now, what we really want to know is how much energy we are saving and how many dollars we might be saving in this process. So, summarizing these values then based upon the number of gallons of diesel fuel we have, I have shown here the existing 4,072, the new one at 3,416. If we subtract the new from the old, we can see here that we're going to have about 656 gallons of diesel fuel savings per year. And if we do this just based upon the differential in cost that we had from beginning at 16,286 compared to the 13,666, that gives us now, we're actually going to be saving about $2,600 in fuel costs on an annual basis. So 656 gallons of diesel fuel and $2,620 would be saved if we switched our system from a 70 psi to a 50 psi system. Now, one shouldn't do this just unilaterally without considering the potential for things to not be designed properly under the lower pressure. For instance, water application systems may need to be changed in terms of the sprinkler package. Going to a reduced pressure sprinkler package on some field sites may generate runoff where the higher pressure one did not. So we need to take these kind of things into consideration as we're suggesting to people that they make these changes out there in the field. But what we really want to know is when we make this change, we can save $2,620 per year, but how much can I afford to spend on converting the irrigation system from 70 psi to 50 psi? And to do that, we need to use what is referred to as a series present worth factor, the accounting numbers that will allow us to convert a series of $2,620 a year payments into one lump sum that we can spend today to cause the system to be changed and improved. So as we look at this, then in my example, I'm using 8% interest, and I want to repay this back in a 6-year time frame. Obviously, when you're doing these kinds of things, you'll be working with the producer and utilizing the numbers that they may be working with, and so you would have to enter this table to get the right factor for their conditions. But using 4.62, then we multiply our 2,620 by 4.62, and you can see here that we're going to generate the savings that would be equivalent to a payment today of $12,104. So if we spent this amount of money, can we make the changes that would allow us to make this switch from 70 psi to 50? What I didn't mention is the pump itself may need to be changed in this, so a lot of times this would be a sprinkler package and a pump that would need to be changed to make this switch from one pressure rating to another. So we have to decide then whether we can pay this back and whether this $12,104 is going to be sufficient to make the payments on the switches that we're going to make, changes we're going to be making. So I guess, Scott, this would be a place where I'd probably interject a stop here when we're doing this for the extension site. We typically stop for questions.
Okay. Well,
but I'm going to move on now for this purpose. And I don't.
Yeah, you don't have to stop. We can put those in later.
Okay. All right. All right. Okay. So moving on then to point 2 of our original plan for today's discussion is to look at some basic pipeline hydraulics. As we look at the irrigation systems that are out there, we have 3 different types of energy that are involved in our irrigation distribution systems. One part is the kinetic energy due to the velocity of water moving through the pipeline. So just by virtue of the fact that water is moving, there's some energy involved in making that water move from one position to the other. The second part is the potential energy due to differences in pipeline elevation. So as we go up and over a hill with a center pivot, there's potential energy that changes within the pipeline system due to that elevation change. For example, each 1 psi change in pivot pipeline pressure is equivalent to 2.31 feet of elevation change. So that means that each foot of elevation change is equivalent to about 0.41 psi in the pipeline itself. So these get accumulated as we go up and over hills and need to be addressed in the original design. The third part is the potential energy due to water pressure in the pipeline. So as we pressurize the pipe in the pipeline, it has the potential to cause water to move vertically up and over the hills and through the pipeline itself. So we need to account for all of these as we're looking at the design of our irrigation system itself and how we might evaluate that. So let's begin that discussion here this afternoon with a discussion about the different types of pumps that are out there and the way these systems might be laid out there in the field. If we look at a centrifugal pump situation, we're going to be pumping water from some surface water impoundment through a pipeline and out through an irrigation distribution pipeline through the center pivot or tow line or some other water distribution system that might be over here on the right. And so as we look at how we're going to do this, we need to calculate some numbers and summarize the potential and kinetic energy that is involved in this system. The first part that we're going to look at is the suction head elevation difference between the water surface that we have in our impoundment or river that we're pumping out of up to the inlet of the pump. And so the HZS here that we're working with is the elevation change between those two parts, and there's a maximum value that we can have for that, and I'll get back to that here in a little bit. The second part is the elevation head, And this is the difference in elevation between the pump inlet and the water distribution system that's out in the field. So this would go from the outlet of or inlet of the pump to the outlet wherever the water comes out of the pipeline, whether it be a nozzle or a gate in a gated pipe system. The third part here is the pressure head. This is how much pressure we produce by using the pump or the energy we add to the water that causes the water to move through the pipeline and through the distribution system and out the other end. The last part here is the friction head. And this really is based upon how much water is moving through the pipeline, what the pipeline material is made out of, and what the diameter of that pipeline might be. And so we're going to talk about this in a little more detail as we go along. The other type of irrigation pumping system is a deep well turbine, and like the centrifugal pump operation, we are going to calculate the total dynamic head here, and we have the lift, which is the depth of the water below the pump outlet. We're going to account for the pressure head in the pipeline by monitoring the pressure at the pump here and multiplying by 2.31, and then we're going to estimate the friction loss just like we would have done for the centrifugal pump as well. And so we totaled those up, and those were be the total dynamic head that we would use to calculate how much energy should need to be used to pump the water. So first thing, let's look at predicting pipeline friction losses, and we do that by starting off with calculating the velocity and velocity head in the pipeline. So if we go to our example of 125 psi pipeline that we're going to be using in this system, in this example, our diameter is going to be the 8-inch inside diameter. 8.095 would be a standard number to use. We have a flow rate here of 850 gallons per minute. So why are we interested in the velocity head? Well, the flow velocity determines the energy that's in the water that we've just discussed. As I mentioned, it's going to help us in determining what the friction losses are going to be. And lastly, and to some degree, maybe the most important part of this whole thing is that we have system design, compliance kinds of things where we want to minimize, if not eliminate, the potential for water hammer in the pipeline itself. And water hammer is a phenomenon that occurs when you get, based upon momentum of water moving in an individual or a given direction, and it comes in contact with a major change in direction, like an elbow or a T, that water might be going horizontal towards the T, and eventually the only direction that can go is vertically up out of the T. That change in direction has to absorb the momentum of the water moving in the horizontal direction. So if we have a long pipeline and at the end of the pipeline we have an elbow, then we have a situation where if the velocity in the pipeline is too high, we can develop a water hammer that could cause the pipeline to fracture and fail. And so there's a number of things we can do to help deal with this, but bottom line is that the velocity is something that we need to consider in the design of the system. So let's just look at this, and we'll talk a little bit more about that as we go along. So the pipeline velocity that we would calculate is based upon essentially a conservation of mass, where we start off with an equation that the flow rate is equal to the velocity times the cross-sectional area of the pipeline. If we realign that and solve that equation for velocity, we get the flow rate divided by the cross-sectional area. And if we utilize a conversion factor that deals with the square foot and gallons per minute kinds of things, and pi in this arrangement, we utilize a 0.409 coefficient in our equation. We put the numbers, the flow rate we had was 850 gallons per minute. Our inside diameter was 8.095 inches. So if we do that math of multiplying that out, we would come up with a flow velocity of 5.31 feet per second. Now that is slightly greater than the 5 feet per second kind of criteria that would normally be in a pipeline scenario, we have many, many systems operating today that the flow velocity is greater than 5 feet per second. The thing we want to have involved in the design of those systems that are greater than 5 feet per second would be some means of distributing the energy that comes with the water hitting the end of the pipeline. So that might be a pressure relief valve. It may also be a situation where we allow air to exit the pipeline in the form of a air relief valve. The pipeline going to the center pivot with sprinklers that allow water to exit along the pipeline of the center pivot would be helpful in this regard. So basically a way for some of that excess energy to be to exit the pipeline itself. The other thing that typically happens is that these systems with long pipelines would have a thrust block that is basically concrete poured around the elbow or T that's on the end of the pipeline that helps distribute some of the force of the water that's hitting the end of the pipeline so that it's less apt to cause the pipeline to fail. So there's a number of things we can do to help deal with this, but bottom line is if we have a short pipeline, it's not too much of an issue. If we have a long pipeline, then we have to deal with some of these other kinds of additional accessories on the pipeline to help us deal with the potential for water hammer. Now, when we move from calculating the velocity to the velocity head, we basically take our velocity and divide it by 2 times the acceleration of gravity. So if we put those numbers into this equation that we have here, 5.31 feet per second, that squared divided by 2 times 32.2, which is the acceleration of gravity, we come up with the numbers of 28.2 divided by 64.4. So our velocity head in this pipeline scenario is 0.44 feet. This number is relatively insignificant when it comes to the overall design of the irrigation system, because we're going to be talking about, in some cases, hundreds of feet of head that we have to provide with the pumping plant installation. So something less than 1 feet is not going to change that design very much, if at all. But like I mentioned, the velocity is still a design criteria and one that we shouldn't overlook when we're visiting with producers. Now, the next part here is to calculate the friction loss in the pipelines, and we're going to do this in essentially 2 parts. As we look at that, the ways in which this is done, I guess first, basically we have the calculation procedures. The most accurate one is the Darcy-Weisbach equation that was developed a long time ago, but it's empirical in nature. The problem is it requires the calculation of a friction factor that is different depending on whether the flow in the pipeline is laminar or turbulent. And it's also based upon, it's based upon the Reynolds number and the absolute viscosity of the fluid. So what this means is, in the real world, is that in order to come up with the actual overall friction loss per 100 feet, you have to go through an iterative calculation in order to get all the components to come out right. And so as a result of all these, it's not something that's used very often because of its difficulty in use. More frequently, we're using the Hayes-Williams equation that I'm showing you here. It is a empirical equation as well. The major assumptions here is that the water flow in the pipeline is less than 10 feet per second, and basically we're talking about the kinematic viscosity of the liquid. It's water at 60 degrees, and most groundwater that we pump through irrigation systems is going to be somewhere in the 50 to 60 degree range, so we're pretty close with that. And it's now the most widely used in the irrigation industry in terms of selecting components of the irrigation system itself. So let's look at the friction loss in the center pivot, and this is different than the pipeline. And the reason is that the discharge per unit length increases with distance from the pivot point due to the fact that we are irrigating more area on the outside of the system than we are towards the center or center pivot point. The other part is that in many of our irrigation systems, the spacing between the sprinklers may or may not be a constant value. So we may not have a spacing of 9 feet 4 inches all the way out from the pivot point to the end gun, there may be some different spacings in there based upon the need to irrigate smaller areas towards the inside relative to the outside. The flow rates per sprinkler are also not constant because of the fact we're irrigating more area on the outside part of the system. So in many cases, the system wetted length may extend beyond the end of the pipe because the sprinkler is irrigating area off the end of the pipeline, whether it be an end gun or just the sprinkler at the very end of the pipe. So we can't necessarily just use the pipeline when we talk about these kinds of things. If we look at the center pivot industry, this table provides the standard pipeline diameters that are available from the manufacturers. In most cases, the standard is a 6 5/8 inch pipe that's highlighted a little bit here in this particular table, which is an inside diameter of 6.375 inches and 161.9 millimeters if you're wanting to do these in metric units. So these are the standard pipeline sizes, but by and large, if you don't specifically ask for something different, you're likely to get 6 5/8 inch diameter pipe, and if you don't have a way of monitoring or measuring that out there in the field, that would be a good thing to assume. So let's look at a system here that has 7 towers on it, and the overall length of the system is 1,320 feet, and we have an end gun at the end. The pipeline diameter is that 6 5/8 inch all the way out. Also assume that we've got 850 gallons per minute coming into the pipeline from the left here, or into the pivot. So how do we then estimate what the friction loss would be in this pipeline? This particular graph shows you, or depicts what I was referring to earlier, in that we still have a lot of flow in the pipeline of the center pivot way towards the outside edge end of the pipeline because of the acres involved. So if we just look at the situation where we're at 1,000 feet and we go out to 1,000 feet, we still have 400 gallons a minute or a little bit more than that in the pipeline being transported out towards the outer edge of the system. So here we are more than 2/3 of the length out, and we still have nearly half of the flow rate still in the pipe. So this is what I was referring to earlier. So let's look at the center pivot losses here. We're going to use the Hayes and Williams equation that I spoke of. This is the equation with the values in here. And so we're going to do this on a per 100 foot of pipeline length. The C factor here is a friction coefficient based upon the pipeline material, and I'll show you a table with those values in it in a minute. Q is the flow rate in the pipeline, or entering the pipeline in gallons per minute. D is the inside diameter of our pipeline in inches. So we've got a bunch of different units here that are accounted for in our coefficient of 0.207 out at front. Now, with this initial look at the design or the estimate of friction loss, we're going to assume that no water exits the pipeline. That's not the real scenario, but we'll fill in the gaps here as we go. So initially, no water exits the pipeline. If we look for the friction factor C value for different pipeline materials, these are the ones that would be the more standard ones that you might see out there in the field. Most center pivots, unless they're special order, are going to be galvanized steel, and that C value ranges from 135 to 145. For our purposes here today, I'm going to use a C factor of 140. And we still have the 850 gallons per minute, 6.375 inches of inside diameter of the pipeline, and no outlets. So if we put those numbers into the Hayes and Williams equation, we're going to come up with the friction loss per 100 feet of pipeline of 3.57 feet. Now, again, this is a scenario where we still have to deal with the fact that we've got end gun on the end of our system that we have to deal with. And so we're going to make some adjustments in this value here as we go along. So this is what we originally dealt with up here on the top. We ended up with our 3.57 feet of head loss per 100 feet of pipeline. And now we need to adjust for the fact that we have an end gun on the system. So we do that by calculating an equivalent or effective hydraulic length of our system, and to account for the fact that we have multiple outlets along the way. So to do that, this equation is the length of our pipeline times the ratio of the flow rate coming into the system divided by the flow rate that would be minus the end gun rate. So Q sub B here in this equation is our initial flow rate minus the flow rate of the end gun. So in this case, Q sub B is 850 minus 75, or 775 gallons per minute. So if we put those numbers into our equation, we find that the equivalent or effective hydraulic length of our system in terms of friction loss estimates is 1,385 feet long. So we now have our 1,385 foot long for our effective hydraulic length, and we go then to the friction loss equation, where we utilize the friction loss in 100 feet of pipe, and we're going to multiply that by a friction factor based upon having more outlets, or having outlets in the pipeline, and multiply that whole thing by our effective hydraulic length. If you look in the literature, there are values for F sub P that have been calculated based upon theoretical values, and they range from 0.54 for a system without the end gun to 0.56 with the end gun. So if we put, I'm using with the end gun in our scenario here, so we're going to put 0.56 in the equation. We had the 3.57 feet times the 0.56 times 1,385, which is our effective hydraulic length. We divide that by 100, and now we're going to say that the friction loss in our center pivot, where water enters the pipe or center pivot pipeline at 850 gallons a minute in a 6 5/8 inch pipe, we're going to have a friction loss of 27.7 feet of head. Now, if we want to look at that in a pressure scenario, we simply take the 27.7 and multiply by 0.433, and we are going to see that the friction loss in our pipeline of the center pivot with an end gun is going to be 12 psi. Now, if the end gun's not running, that value drops to about 2 psi or somewhere in there. So, but if the end gun is running, the overall friction loss is going to be about 12 psi. That's a pretty standard number for systems that are out there. That previous example was based upon having one pipeline size in the center pivot. Because there are different sizes available, one of the ways in which people deal with excessive friction loss in the center pivot itself is to put multiple size pipelines on the pivot itself. This is particularly used in systems where there might be extremely long, and I'm going to say in excess of 2,000 foot long systems, oftentimes will have more than one pipe size on the system, and sometimes may have 3 different pipe sizes on the lateral to try to reduce the friction loss and maintain pressure in the pipeline while keeping the cost of the original system pretty much under control. So let's look at a system here now that the spans 1, 2, and 3 are installed with 8 and 5/8 inch pipeline, and spans 4, 5, 6, and 7 are the same 6 and 5/8 inch pipeline that we used previously. Now, the way this is different is that we simply take the friction loss of our small pipe that we've calculated previously, and we multiply it by the K dual factor. And this K dual factor is a reduction factor based upon the differences in pipe diameter between the large size and the small, and how much of the center pivot length has the different size pipelines on them. And so we'll go through that calculation to come up with then the friction loss in the combined system. So the K dual that we had in that previous equation is based upon this R over L factor that's in this table. R over L is the portion of the system length with the larger pipeline diameter. So in our case, we had 3 spans that were of the longer length and 4 spans that were of, 3 spans were of the larger diameter and 4 spans were of the smaller diameter. So if you do the math, we end up being somewhere between 0.3 and 0.4. Actually, it's 0.36, that number turns out to be. And so we go over to our table under the 8 5/8 to 6 5/8 inch pipeline, and you can see that we're between 0.51 and 0.61 on the table. So we'll have to interpolate to get that value, and if we do that, we end up with a K dual factor of 0.55 that we'll use in our calculations. So we put that 0.55 in our equation, which means that the friction loss in the dual pipeline system would be 0.55 times 27.7, or we would end up with 15.2 feet of friction loss in the pipeline. This is compared with the 27.7 feet we would have for the single pipeline diameter system. Converting that 15.2 to PSI would be 6.6, so we're just a little over half of the friction loss that we would have had in a smaller pipe system. So now what we want to do is find out whether it's going to save us any energy and whether we can afford to put the different size pipeline out there to get this job done. So we're going to look first at the mainline friction loss here that we're going to use the pipeline to get the water out there. So we have this pipeline that I'm using in this example that is 1,500 feet long. We're going to use 125 PSI rated pipeline, PVC. We're going to include 4 8-inch 90-degree elbows and 1 8-inch gate valve, just to provide you with the idea of how we would make those kind of calculations. Most systems are going to have a couple of elbows in them, and not all of them will have a gate valve involved, but to go through the math and how the process works, I'm putting them in the system here. We still have the 850 gallons per minute, and our pipeline coming from the outlet of the pump to the distribution system now is going to be 8-inch diameter. So first of all, we want to do the friction loss in the 1,500 feet of pipeline, and then we're going to add to it the friction loss associated with the accessories, the elbows and the gate valve. Now, to come up with the friction factors for these different pipelines, one can measure these kind of things in the lab, but it's already been done by the manufacturer, and these values are used pretty extensively in terms of equipment selection and pipeline designs. This particular one comes off of the internet and from the Diamond Plastics website. And there's a couple things I would mention about this particular chart. On the left-hand side, we have the flow rate in gallons per minute increasing in value going down the page. And then we have 4 different types of pipeline in terms of pressure rating across the top. And lastly, if you look down here at the bottom, we've got some values that are highlighted. These values are the flow rates for this type of pipe where the pipeline velocity is 5 feet per second or greater than 5 feet per second. And so these are the design maximum flow rates, if you will, if you do the design based upon the 5 feet per second criteria. In our case, if you remember the calculation, we have 5.31 feet per second, and so our value is just close to the bottom of our chart here of 0.999, or essentially 1.0 is the factor that we would use. Now, to get the accessory kinds of friction loss numbers, we're going to look underneath our 8-gallon per minute pipeline size here in this column. The flow velocity that we calculated in the 8.095 inch diameter pipeline was 5.3 feet per second. And we look down below here, and you can see that for different types of fittings, we're going to have different factors. Now we talked about using the 90-degree elbows, so we're going to use this 0.12, and we also had a gate valve that we're going to use at 0.03. So we're going to use these values coming out of this chart to do some calculations. So the friction loss in the pipeline, we had 1,500 feet of 8-inch pipeline multiplied by the friction factor 0.999 divided by 100, because we want this per 100 feet of run. And so we have 15 feet of elevation change, or 15 feet of friction head to get the water through that pipeline. Now we want to then calculate the friction loss in the 4-inch of the 4 8-inch elbows. So we multiply 4 by the 0.012 that came from the table, and then we have the gate valve. We have one of those times 0.03. Add those two together, and we have an additional 0.51 feet of friction loss through those accessories. So we're going to want to add those two numbers together to get the friction loss in the pipeline. And for some reason my line's out of place here, but the loss in the distribution line is 15.1 feet. The loss in the pipe fittings is 0.5 feet, and the loss in the center pivot of our original 6 5/8 inch diameter pipeline was 27.7 feet. And so we have 43.3 feet of friction loss in our pipeline. That's a system where we use 8-inch pipeline and 6 5/8 inch delivery pipe on the center pivot. Now we go to our multiple diameter system. I'm going to use a larger diameter pipeline here, so we're going to use 10-inch diameter pipe. It's still 1,500 feet long, still 125 psi pressure rating, and we're still going to have the same accessories and flow rate. So now we want to do the calculations that are listed under the find here, the friction loss in the pipeline and the accessories, just like we did before. We go on the same table that I showed you earlier from Diamond Plastic, but now for 10-inch pipe instead of 8-inch pipe, we have at 850 gallons per minute. You can see now that we're well below the 5 feet per second because we're above that highlighted value in this column. So at 850 gallons per minute, a 10-inch line, our friction factor would be 0.342. Again, we go to for 10-inch diameter because we got that for our accessories. And you can see here for the regular elbow, we got 0.05. And for our gate valve, 0.01 that we're going to use for the accessories to figure out what the friction loss is there. So we go through our calculations again, 1,500 feet times 0.342 feet per 100, and we end up with 5.1 feet of friction loss in the delivery line. And then for our accessories, we are at 0.21 feet if we do the math here. So you can see that these numbers are considerably lower than what the ones were for the smaller diameter pipe. The question is whether we can afford to change the pipe diameter with savings in energy costs that we might generate. So like the other one, we're going to add these values up. So we have the loss in the distribution line of 5.1. We have the loss of the pipe fittings of 0.2, the loss in the center pivot 15.2. So now the total is 20.5 feet of friction loss in our system, which again is about half, a little less than half of what the previous one was. The equation that we're going to use here now is to calculate the water horsepower, because that's what we really do use when we're figuring out what the energy cost is going to be. And so as we look at this then, the water horsepower hour calculation is based upon the pressure or total dynamic head that's here, the pressure plus the lift. We're going to multiply by the flow rate here, the time of operation, and our fuel cost that we have here. And then we're going to divide by 3960, which is the coefficient to convert all these numbers to the right units. And we're going to multiply and also divide by the Nebraska Pumping Plant Performance Criteria for diesel fuel. So if we put the numbers in our equation, we're going to have 43.3 was our original one. We're going to do this a shortcut by just looking at the differences here, by the way. In our initial installation, we had 43.3 feet of head loss in the pipeline, and we had in our new one with the larger and multiple size pipelines 20.5 feet. So what we really get here is the difference in water horsepower hours required because of the friction loss in the pipeline. All other things that we had associated with our system, basically, we're assuming that they're going to be the same. So they're not going to enter into the mix. But if we do this calculation, the water horsepower hours that we're going to get here and the cost of fuel that we're going to get associated with it is $1,566 per year by multiplying by the fuel cost that we're going to have here. Now, these numbers have all not included the pipeline or the pipeline installation cost. So whenever we're talking about changing some of these systems, that installation cost and the pipeline cost differences themselves need to be considered. And I've not entered them into the discussion today because they vary quite a bit depending on the price of oil and the price of the pipeline and the availability of installers and all this kind of thing. And so everybody's going to have their own kind of local numbers that they can put in there for that particular one in a process of doing this analysis. Again, we want to take that number that we had for savings on an annual basis and convert that to something that we could spend today and recoup over a period of time. For purposes of our example today, this being an installation of a pipeline system and a distribution system, I'm going to assume that I'm going to want to recoup this investment in a longer period of time because this pipeline and system is going to be there for quite a while. It's different than what you might expect for some of the other components that we might deal with. So that's one way to consider it anyway. And if we go for a 10-year period at the same 8% interest that we were dealing with earlier, our multiplier or our series present worth factor is 6.71. So if we take our $1,566 and multiply it by 6.71, you can see that we're going to be able to potentially invest $10,508 today and pay it off with a series of $1,566 per year payments over a 10-year period. And if we can make the changes necessary in the system for less money than this, it's basically should be considered maybe a go. If it's more than this, then obviously one has to consider whether it's worthwhile doing or not. And quite honestly, that's been the issue for this type of thing in terms of changing pipeline designs after they are installed in the field, is that the cost of making a change generally is greater than the cost savings that you're going to get by doing it. But in the process of doing these energy audits, we should take a look at this in terms of what they could do in terms of energy savings by changing pipeline sizes and other components in the system. And we've talked about the pumping plant part of it. We've talked about irrigation scheduling, which is management, and this is kind of the distribution system part of it, and we should consider this as well. So it's not to be downplayed. In summary then, really the most significant energy conservation that we can do in an irrigation system that's already in place might be reducing the center pivot operating pressure or the irrigation system operating pressure in general. Now this has to be taken into account based upon whether or not that change in the system pressure is going to cause other operational problems that are more significant than the energy conservation might be. One of those might be whether we generate runoff with a center pivot application, whether we're affect our water application uniformity of a tow line system per se. So these are the kinds of things that should come into play. Velocity in the system design is basically a criteria that should have been used in the original pipeline design. 5 feet per second is the typical criteria. If the flow velocity in the pipeline is greater than 5 feet per second, then we should be looking for ways in which the excess pressure is allowed to escape the system during startup, because startup and shutdown are the two periods of time when there's a fairly large change in velocity as you water hits the end of the pipeline, or we have a change in flow coming from the pump itself. Pipeline friction losses, we can estimate them quite easily with the Hayes and Williams equation, and these should be considered to be estimates because they're based upon a friction factor for a pipeline material, and in particular for steel and aluminum and other metal kinds of pipelines. They tend to oxidize some in the inside, and that would result in a friction factor that could be slightly different than the one that's being used. And so the best way to do that is to actually use a pressure gauge at different portions of the pipeline while it's operating to verify that these numbers might be accurate. And that's certainly a way of verifying the original design of the system as well, is to go along the system and attach a pressure gauge at various locations to verify that the pressure is what it's supposed to be at the different locations. The main line and minor fitting losses can be used to estimate how much energy can be saved and how many dollars could potentially be saved in pumping the irrigation water through the pipeline during irrigation events. And you then look at those costs and compare them to the cost of changing the installation to determine whether it's cost effective to upgrade the system into a different design. Comparisons between different installations, basically we're going to look at the friction losses as inputs in the pump energy equation, and that can be used then to determine how many dollars can be saved by making the switch. So those are the sorts of things that I'd share with you this afternoon.
Bill, one question when you were talking about the main line and checking it with pressure gauges, would you put a stub pipe stub up with a valve on it so you can do like a quick coupler along the line to check it?
Well, I think that one can use the pressure gauge. Most of our systems, at least the ones that we have in Nebraska, will have places where one can attach a pressure gauge. One at the pump outlet, our mainline check valves we use for chemigation, and most systems have on them anyway, have an outlet that you can attach a pressure gauge to it, even if you have to use an adapter to get to a faucet type of thread, but you can do it there. At the pivot point themselves, there's generally a drain plug or other access point where they would put a pressure sensor in that one could potentially use. On the pivot pipeline, each place where a sprinkler comes out, one could attach a sprinkler to it. Now, these kinds of things tend to be either screw them in place and have several of them on hand and screw them in different places and go along and after the system is in operation and record them, or go along and place them in the outlet as best you can. But the sprinklers are going to be operating there, and sometimes it's difficult to do it while the system is actually running. So my sense of it is that the best scenario would be to have 3 or 4 that one would put on the system in different places, and then start the system up and record those values afterwards, and then later go back and remove them.
Okay.
There are ways, as you mentioned, Scott, to check that pressure maybe a little less accurately, but still you can do it on the sprinkler itself and other components by attaching fittings while the system is running. But I personally try to stay away from that.
Yeah, I guess I was thinking you'd do it before you started the system, but have a stub shaft with a valve on it so you could, I don't know if you'd want to use the same pressure gauge throughout, but I guess if they're calibrated, it wouldn't matter. Yeah.
Either way, I guess you go through and put those stubs on and move the gauge, or just have a separate gauge and don't worry about turning them off.
Okay. All right. Well,